I wanted to make a video here to show you what I did with an igbt driver for a flyback. This has been an ongoing thing for a long time. Let me see if I can get that to pan out some. I got this all setting under a 100-watt light bulb. My lighting is really bad, so I hope it's tolerable. But I have about probably 300 hours into building this, and the design of it is fairly incredible. But the performance of these IGBTs leave a lot to be desired. The switching transistors I was using before are, I guess you could say, a little bit more efficient, and you can get higher power levels at a lower voltage. But without spending 6 days talking about that, I just want to show you what I did here, because this thing is a semi-masterpiece of something. I'm just not sure what. Let's see if I can get all this in. This is the flyback there. It's an amazing 1,000 turn flyback on, I guess, what you would call their standard cores, which are like somewhere around 625, I think, about 5/8, maybe just a little under. They're not the biggest core I've ever used, but it's a 1,000 turn core with an 8-turn center tap primary. And I did basically the same thing that I've been doing on these, is wind a double layer of number 16 Litz wire, and right here's my primary going down to the barrier strip, and there's 4 pieces of number 16 hitting here, and I have another coil for it too that I wound as well, to take the voltage down a little bit. But this was going to be for a voltage multiplier that after a year of futzing with this thing, I just said enough is enough, and I'm not going to build another voltage multiplier ever in my lifetime. Because you can't get parts anymore, and even if you could get them, they would be so expensive you'd never be able to afford them. So it's a pricing and availability issue. There's nothing spectacular about this. There's no point in me powering this up to show you, because, I mean, if you're watching this video, you know what 15 kilovolts looks like. The important thing to me was I wanted to show you the design and the layout of it, because I'm pretty proud of that. I have an insane amount of time and thought into this thing, and I wanted to keep it as compact as I could. So you can see I kind of layered everything and have it all sandwiched together. There's a 5-volt fan down here which runs high speed at like 357 milliamps, that I had to get this FR4 board cut out for, which is a huge problem to cut this FR4 board, because it's like almost 2/10 of an inch thick. It's just crazy with what you have to buy in order to cut this stuff. But you can see it's layered. There's actually a shield in here between the side of that fan and the primary, because I didn't know if that fan was going to lock up off of any magnetic field, and it probably wouldn't have. But, you know, I wasn't willing to take any chances and having that fan go up and down, because I've seen that happen before. So I bent a steel shield in here that was bent out of a 4x4 electrical wall plate. And hopefully you can see in there. There's a 5-volt fan. And coming around here, as I wrap this up into one big mess. There's two snubber caps here, and I wanted to layer everything and compact it as much as I could. I had to custom make this little heat sink out of some angle and cut it all out with a jigsaw and file it down and polish it and stuff. But anyway, I got a 25 watt Dale here, snubber resistor, which is a 15 ohm, and then I have a 12 watt MRA, which is a 15 ohm. So I have 7.5 ohms in series with these 047s. And if I take the resistor up on these resistors will actually over dissipate. Which brings me to something I read on the internet one time. Somebody said about if their snubbers are getting too hot, reduce the caps. Well, that's true to a certain aspect, but also by the same token, if you raise the resistor, your resistor is going to dissipate more. Just in case you didn't know that. So if I pull these 15s off across them, these 25 watt Dales will probably be close to dissipation. But the nice thing is, with the proximity of the fan, it knocks the heat down on that heat sink pretty good. And there's actually a thermistor on it as well, over here in the corner. Back to the highlights. There's a snubber here across my 68 microhenry choke with this Dale 25 watt here and that reverse bias diode. And then coming off the power supply side of the choke, I had some leftover low ESR caps from some audio amps. So I just made a little energy storage board. It actually needed about 1,000 microfarad more than I had, but that was what I had to work with. So I used it anyway. But I just mounted them all on a piece of FR4 board, ran some solder wick down the sides, and brought some 632 brass hardware through, and some good quality ring terminals. And then I have standoffs holding that whole thing up. And flipping it around, I wanted to tell you about the special things that I built into this, because I think that's what makes this a pretty cool build. This is a overtemp lockout relay, which is just the old style, like what I used to call the Bosch relays, the automotive relays, that take a boatload of current to pull in the primary, like 130 mils anyway. And I just started taking all the parts I had at hand and incorporating them in the best possible way that I could. So I ended up with a over temperature lockout, which works absolutely beautiful. If this heatsink were to ever hit like 60 degrees C, which is pretty darn hot, probably like, what is that, 150, 160 Fahrenheit, might even be 170 Fahrenheit. No, I think it's like 150 Fahrenheit. But anyway, that'll lock this whole thing out, and nothing will power up until the temperature falls back down. And there's all kinds of safeties and stuff where you had to be careful which regulator you were connecting to. Not really safeties, but you had to be extremely clear-headed on where you were taking power sources from, because you could create a paradox. If you understand what I mean by a paradox, where a certain circuit would shut down power to another one and cause itself not to work in the first place, if that made any sense to you. I know what I mean, I just have a hard time communicating. So anyway, this little barrier strip here hits ground up here, and it also hits both collectors of the IGBTs. There you can see the thermistor, and there's a 2 amp primary fuse here, which all the regulators are fused through, and also the coil of the over temp lockout. So no matter what could ever possibly short, it's no big deal. And getting to the guts of it all. Oh my. I left these standoffs on here. That way it's not jarring this flyback around. I had to make custom brackets, and I had to cut threaded rod and everything to go through there, and there's a piece of 1/4 inch by 1 by 1 angle that's extremely overkill that I use for mounting that flyback. And I used some pieces off of some old vintage flybacks to fabricate the whole thing together, but it's extremely solid. Power hits this LM317 up here basically first out of everything, and oh my, I have no idea if you can even see this. There's an LM317 here which just forms this voltage regulator sitting here on this board, and that adjusts from 1.8 to 6.5 volts. The voltage adjustment pot here actually doesn't have a series resistor in it, so it will turn the whole way down to ground, but it actually can't go to ground because I have a forward bias diode, so there's a diode drop below the pot. So that sends my 6.5 volts I need here to these gate drivers. And I'm not even going to attempt to read them because every time I try to do that I fail at it. But I'm sure if you're familiar with gate drivers, you'll know exactly which ones these are. They're the UC somethings that I can never remember. And then I have these infineon, excuse me, IKW50EES5s, if I'm looking at that right. And boy, I'm not sure I really want to make too many comments about them, but you know, it does work well. You know, the problem is you just have to turn the voltage up a lot higher than what I'm used to with NPN switching transistors. These IGBTs got really shitty saturation to them, and it doesn't matter which ones you buy. I think I'm not sticking my foot in my mouth by saying this, that every single IGBT they say is low saturation is not low saturation by my standards. And here's our old A-stable 2 transistor oscillator that always runs, and the frequency control pod here, just this from, let me see, it was, I think it was 23 to about 35, ballpark, somewhere around there. It's set on 28 kilohertz. So there's your A-stable that toggles back and forth, and then that jumps over here and hits this relay. And you say, why a relay? Well, I was concerned at what happens if this 5-volt regulator that's feeding this A-stable here suddenly just croaks, or your voltage slumps coming in, or Lord knows what could happen to make this voltage here drop off, and your duty cycle change, and a whole series of cataclysmic results could happen. So I took my outputs off of these switching transistors and fed it into this relay, and then came out on the normally open contacts and hit the gate drivers. So if things are not what they need to be, the gate drivers won't get no signal. Oh my. Now, here's the other mess. I also sandwiched a thermal board down here. I am all over the place today. There's so much in this, I just don't even know what to tell you. There is a thermal board down here, which has a comparator on it, an adjustment pot, and some other stuff. I packed it so tight, I literally had to epoxy the back side of this board because my connections were, I'm guessing, probably 20 thousandths of an inch apart. There is so much stuff on this board. So I epoxied the whole back side of the board because there's nothing on it that can possibly die, and I was not taking a chance. It's probably the most micro miniature stuff I've ever done. The only flaw that I did have was I ended up with my temperature adjustment pot down here in the corner, and it's a top turn pot. So I made one mistake, but I wasn't sure where I was going to end up mounting this temperature board. But anyway, this adjustment pot goes from 40 to 50 degrees C on this thermistor, which I did have up here on this heat sink. That's another story. So I can adjust the trip point for that fan anywhere from, I think it's 104 Fahrenheit to like 122, I'm thinking is 60 degrees C. I'm thinking it's somewhere around 122 Fahrenheit. And the fan toggles off and on perfectly. It's got just the right amount of hysteresis on it, so there's no chattering, and it's not excessive where the heat has to drop down extremely low in order to make it turn off. It's pretty tight. So the hysteresis that I used worked out very well. And there's a separate 5-volt regulator down here on the thermal board too. So we actually have 1, 2, 3, 4. We have 4 voltage regulators. 3 of them are 5 volters, and the one is an LM317. And I was running out of space, so I had to do some kludging onto this board. This comparator here is a CA3130 op amp, and I used that to sense the voltage not only on the gate drive regulators but also on the 5-volt to the oscillator board, which is about a 3-day story on how I did that. But this is the trip point, so this thing has under voltage lockout as well. If the voltage drops down on the output of this regulator such that it causes the duty cycle of this to futz up, or the amplitude of this to futz up, it'll kick the whole thing out and lock it out until your voltage comes back up. And it will also kick out the voltage and lock itself out if the voltage to the gate drivers is such that it will not allow these IGBTs to have sufficient gate drive voltage. So it actually does 2 or 3 different things altogether. But strangely, it only has one input. I managed to not use multiple comparators to monitor more than 2 functions, really. So we got over temperature lockout, we got fan on and off, adjustable, and we got low voltage shutdown, all incorporated into this, and it works absolutely beautiful. I could probably talk about this for 6 days and feel like I didn't say enough. It works very, very beautiful. It takes up about an 8-inch footprint, and it would occupy a space about 12 inches tall. I can can back this up some. So from the table to the top, it's going to run 12 inches. What I was going to do was make a cage out of this 1.25" angle, 1.25" by 1/8, an 8x8 cage, 1 foot tall, and plop this in the middle of it on a base. And then I was going to sheet the perimeter of the cube with plexiglass, and of course pull my high voltage out of the top of the cube and then go into my voltage multiplier pipe. But like I said, I'm not gonna pursue the voltage multiplier at this point. But the whole thing works very beautiful. It works great. It doesn't have one single glitch to it at all. And it's kind of sloppy on top, but everything's really solid. Any place where something wasn't really quite up to power, I used a little bit of epoxy to cheat to make sure there was no chances of, you know, a close spacing shorting out on me over time without me realizing it. There's actually a bypass chip on the VDD to these gate drivers, and I don't know if you can see that or not, but it's a low ESR chip, and I kludged it across the power line there, and I epoxied over top of it. That way, in case I ever bumped it, the ends of the chip didn't snap off. And I made that base out of 1.25" by 1/8 and polished it up, notched it out. I cut all that aluminum out with a jigsaw, which was a killer thing to try to do. To rip down the length of that aluminum with a jigsaw was very painstaking. And then I sanded it all out, ground it out, polished it up. There's actually a board down here that I didn't talk about. That's a power line filter, and that's for the thermal board. And the fan toggles on and off beautifully, and it has no glitches. So I thought maybe somebody would like to see this and get some ideas, maybe, on layering a project, because that's what this was. A big, huge layering process. It worked out really good. I appreciate you watching, and I hope you enjoyed seeing this. Thank you.